Hi everyone, so we're going to start chapter 4 and it's titled Reactions in Aqueous Solutions. We're going to begin by studying the properties of solutions prepared by dissolving substances in water, which are called aqueous solutions. These type of solutions can be classified as non-electrolyte or electrolyte, depending on their ability to conduct electricity. Alright, let's start. Let's go over some general properties of aqueous solutions. So first of all, let's define what a solution is. A solution is a homogeneous mixture of two or more substances. These two substances are the solute and the solvent. Now the solute is the guy that's present in smaller amounts. So the eye of the solution, there's two things. One is in greater amounts and one is in smaller amounts. The one that's in smaller amount is the solute. The solvent is the one that is in larger amounts. Okay, so that's the one that's used to dissolve the solute. Some examples that I can give are a solution would be like a soft drink, your Coca-Cola. The solvent in your soft drink is water. That's in greater amount. The solute would be sugar and carbon dioxide. So basically sugar and carbon dioxide are dissolved in water. Another example I can give is air. In air, you have the greatest amount component, which is nitrogen, and you have your solutes, which are oxygen, argon, methane, and lots of other components, but I only included these. In the beginning of the video, I mentioned that aqueous solutions can be classified into two different things, non-electrolyte or electrolytes. First, let's talk about an electrolyte. An electrolyte is a substance that, when dissolved in water, results in that solution conducting electricity. A non-electrolyte is completely the opposite. It does not conduct electricity when dissolved in water. An easy example I can give you is if you put a pair of inert electrodes, copper or platinum or whatever, and you immerse those inert electrodes into a beaker of water and you add certain things, for that light bulb to shine, you must create a current. All right? A current must flow from one electrode to the other to complete that circuit. So an electrolyte would be if I put something like sodium chloride. Sodium chloride, the salt, is an ionic compound. And when you put that in water, it breaks up into sodium ions and chlorine ions. They dissociate, all right? So it basically sets up an electric current that is equivalent to the flow of electrons in a metal wire. Because the NaCl solution conducts electricity, we say that NaCl is a strong electrolyte. A characteristic of a strong electrolyte is that the solute, such as NaCl, completely dissociates. So it's 100% dissociated. So if you were to analyze that water solution, you put the salt in the water and then you analyze that water solution, you will never find NaCl together as the ionic compound. What you will find is only the ions, Na ions, Na plus ions, and Cl minus ions. So they're completely 100% dissociated. An example I can give for a non-electrolyte is sugar. When you dissolve sugar in water, nothing happens to the sugar. All right, sugar stays as sugar. It does not dissociate into ions. Therefore, the light bulb will not light up because there is no complete circuit there because there is no ions flowing from electrode to electrode. On the other hand, there are certain acids that, such as acetic acid, we've heard of acetic acid with the souring of wine. It gives vinegar, acetic acid basically gives vinegar the tart flavor. And when you dissolve acetic acid in water, it does not ionize completely. If you were to analyze that water that you've put acetic acid in, you would find some of the molecules remain as acetic acid and some of the molecules are as ions. That's what we call a weak electrolyte. Something that is not completely dissociated would be a weak electrolyte. And that's why you see the light bulb is very dimly lit, not as strong as when you saw the strong electrolyte with the NaCl. The ionization of acetic acid, if we were to write it down as a chemical equation, you see here that I've used a double arrow. All right, so the double arrow shows that it's a reversible reaction. What that means is that the reaction can occur in both directions. I mean, initially you have a number of acetic acid molecules that break up into acetate and H+. But as time goes on, those acetate and H+ ions kind of come back together and they become acetic acid again. So this reaction can go backward and forwards, and that's why when you were to analyze that solution, you would find both. You would find acetic acid molecules and you would find acetate and H plus ions as well. One common type of reaction that occurs in aqueous solution is the precipitation reaction. All right, a precipitation reaction results in the formation of an insoluble product that is called a precipitate. So for example, on the left, I'm showing you a picture of lead nitrate, which is a liquid, it's an aqueous solution, and sodium iodide, which is also a liquid. So when I put those two liquids together, they form a solid, which is called lead iodide. And that's that yellow substance that you see coming out of the solution. So that's what I mean by a precipitate is formed, right? A precipitate means that a solid is coming out of the solution. You will be responsible for being able to predict whether a precipitate will form when two compounds are added together. There is a table on page 122, it's table 4.2, which talks about solubility. Solubility rules for common ionic compounds. And if you look at that table, you will see that lead iodide is not soluble in water. So that means it will always precipitate out of water. So if you ever make something that's lead iodide, you should know that that's a solid. You do not have to memorize table 4.2. That table will be given to you, but you need to understand how to read that table. All right, so we will go over that table in class because it's a little bit counterintuitive. All right, so let's go over what these different types of equations mean. So on the top, we have an equation which is called the molecular equation. This molecular equation includes everything, includes the formulas of the compounds as though all the species existed as molecules or whole units. So a molecular equation is useful because it identifies the reagents that you have, like lead nitrate and sodium iodide. One thing I forgot to mention is that from now on, it's very important that we include the states of the formulas that we're using. So for example, lead nitrate is aqueous. That tells me that when you put lead nitrate in water, it's going to dissociate into its ions, into Pb2 plus ion and NO3 minus ion. So it's very important that we include those states, whether it be aqueous, solid, liquid, or gas. And again, you will not have to memorize whether they're aqueous or not. That's why you have the table. But you need to learn how to read that table. All right, let's move on. So like I said, the molecular equation basically tells us everything that is in the reaction. And as pointed out earlier, the ionic compounds will dissolve in water, so they break apart into their component cations and anions. The next step would be to find the ionic equation. The ionic equation is just basically breaking up everybody into their respective ions. Those formulas that can actually be broken up. So for example, anything that's aqueous can be broken up into their respective ions. But if you notice, the PbI2 remains the same because it's a solid. You cannot break it up. So, but everything else is aqueous. So you break up everybody into their respective ions for the ionic equation. And then once you do that, you notice that you have things that are exactly the same on both sides of the equation, both sides of the reaction. So you have 2NO3 on one side and you also have it on the other side. So you can cancel anything that is the same on both sides. And you end up with something that's called the net ionic equation. This equation shows only the species that actually take part in the reaction. So what that means is that sodium and nitrate are just spectator ions. So they're not really involved in the overall reaction. Really what's involved is just the lead and the iodide. We will go over how to do these different types of equations and how to figure them out using the table 4.2 in your book. But you will have to be able to do these on your own. You will have to know how to get from a molecular equation all the way down to a net ionic equation and specify which ions are spectator ions. It's not difficult, it's just you have to learn the steps, just like everything else. Last section I want to talk about in this video are properties of acids and bases. We define acids as substances that ionize in water to produce protons or H plus ions. There's several different definitions for an acid. For example, there's an Arrhenius acid and there's also a Bronsted acid. I want us to concentrate on Bronsted acids. Some properties that you can read here are they have a sour taste. For example, vinegar owes its taste to acetic acid. Citrus fruits contain citric acid, so they do have a sour taste. They can cause color changes in plant dyes. Acids also react with certain metals to produce hydrogen gas. For example, hydrochloric acid plus magnesium, which is a metal, will produce magnesium chloride and hydrogen gas. And they also will react with carbonates and bicarbonates to produce carbon dioxide gas. For example, hydrochloric acid will react with calcium carbonate to make calcium chloride, which is a salt, carbon dioxide, which is a gas, and water, which is liquid. And that's the picture that I'm showing you on the right. And of course, we know that aqueous acid solutions will conduct electricity because they dissociate completely into ions. So the definition of a Bronsted acid is that it's a proton donor. They donate protons in water. Some common acids that we use in the laboratory include hydrochloric acid, nitric acid, acetic acid, sulfuric acid, and phosphoric acid. There's different types of acids. We have monoprotic acids, which means that each unit of the acid yields only one hydrogen ion upon ionization. We have diprotic acids, which means each unit of the acid will give up 2 hydrogen ions. And then, of course, we have triprotic, which give up 3 hydrogen ions. Some examples for the monoprotic acids are hydrochloric acid, because it's only one H, HCl, nitric acid, or nitric acid, which is HNO3, there's only one H. Some examples of the diprotic would be sulfuric, that's H2SO4, and an example of the triprotic would be phosphoric acid, which is H3PO4, so it gives up 3 protons. Now let's talk about bases and some properties of bases. So a base is a substance that ionizes in water to produce OH-, so a hydroxide ion. The definition of a Bronsted base is that it's a proton acceptor, so it accepts protons. Acids donate protons, bases accepts protons. So I have this little cute definition that I use to remember what a base and an acid does. I call it the BAD definition. Base accepts, acid donates. It's a BAD definition. Pretty corny. But anyway, so bases have a bitter taste. Most of them feel very slippery on your fingers. And for example, some soaps or many soaps contain bases. They also can cause color changes in plant dyes, and of course, an aqueous base solution will conduct electricity, again because they dissociate into ions. Some examples of common bases are ammonia, which is NH3. This accepts a proton and becomes ammonium ion. And of course, hydroxide, the OH- ion. This will accept a proton and become water. You need to carefully read over section 4.3, which goes over acid-base reactions and the properties of acids and bases. You need to become familiar with the common bases and the common acids. In the next video, we're going to talk about what happens when an acid and a base react. All right, see you later.